Finding a balanced flow. We will show that the following algorithm, which uses a divide and conquer strategy, finds the balanced flow in the given network in any polynomial time. As stated above, we will assume that this network satisfies the invariant, i.e. S, A union B union T is a mean cut in N. Continuously reduce the capacities of all edges that go from B to T, other than those edges whose capacity becomes zero until the capacity of the cut. The set of S union A union B and the set of T becomes the same as the capacity of the cut, the set of S A union B union the set of T. Let the resulting network be M prime, and let F prime be a max flow in M prime. Find the maximal ST mean cut in M prime, say ST, with little s in capital S and the little t in capital T. Case 1. If capital T equals to the set of little t, then find a max flow in M prime and output it. This will be a balanced flow in N. Case 2. Otherwise, let N1 and N2 be the subnetworks of N induced by S union the set of T and T union the set of S, respectively. Observe that N1 and N2 inherit original capacities from N and not the reduced capacities from M prime. Let A1 and B1 be the subsets of A and B, respectively, induced by N1. Similarly, let A2 and B2 be the subsets of A and B, respectively, induced by N2. Recursively find balanced flows F1 and F2 in N1 and N2, respectively. Output the flow F equals to F1 union F2. This will be a balanced flow in N. Lemma 5.6. F is a max flow in N. Proof. In the first case, capital T equals to a set of little t. The algorithm outputs a max flow in M prime. This flow must saturate the cut, the set of S union A union B, and the set of T. However, since the capacity of this cut in M prime is the same as the capacity of the cut, the set of S A union B union the set of T, by the invariant, this is also a max flow in N. Next, let us consider the second case. Since N1 and N2 are edge disjoint networks, F equals to F1 union F2 will be a feasible flow in N. We will show that F must saturate all edges from S to A, and therefore by the invariant, it is a max flow. Let G be a max flow in N. Observe that N prime and hence N cannot have any edges from A1 to B2. Therefore, all flow of G going to A1 must flow via B1. Therefore, the restriction of G to N1 saturates all edges from S to A1 in N1. Therefore, so must F1 since it is a max flow in N1. Let F prime be a max flow in M prime. Since ST is a mean cut in M prime, F prime must saturate all edges from S to A2. Furthermore, all flow of F prime going to A2 must flow via B2, i.e. the restriction of F prime to flow going through A2 is a feasible flow in N2. Since F2 is a max flow in N2, it must also saturate all edges from S to A2. Hence, F saturates all edges from S to A in N and is therefore a max flow. Lemma 5.7. F is a balanced flow in network N. Proof. We will show by induction on the depth of recursion that the max flow output by the algorithm is a balanced flow in N. In the base case, the algorithm terminates in the first case, i.e. capital T equals to the set of T. The surplus vector is precisely the amounts subtracted from capacities of edges from B to T in going from N to M prime. Clearly, this surplus vector makes components as equal as possible, thus minimizing its L2 norm. Next, assume that the algorithm terminates in the second base. By lemma 5.6, F is a max flow. We will show that it satisfies property 1 and is therefore a balanced flow. By the induction hypothesis, F1 and F2 are balanced flows in N1 and N2 respectively, and therefore property 1 cannot be violated in these two networks. Let R be the residual graph of N with respect to flow F. We only need to show that paths in R that go from one part to other do not violate property 1. As already observed in the proof of lemma 5.6, there are no edges from A1 to B2 in N, and therefore there are no residual paths from J in B1 and I in B2. There may, however, be paths going from J in B2 to I in B1 in R. We will show that for any two nodes I in B1 and J in B2, gamma I of N F is less than gamma J of N F, thereby establishing property 1. First, observe that by the maximality of the mean cut found in N', all nodes in B2 have surplus capacity greater than 0 with respect to flow F' in N'. All nodes having surplus 0 must be in a B1. Therefore, the same amount, say X, was subtracted from the capacity of each edge, IT, with I in B2, in going from network N to N', we will show that gamma I of NF is greater than X for each I in B2. A similar proof shows that gamma I of NF is less than X for each I in B1, thereby establishing property 1. Let L be the set of vertices in B2 having minima surplus with respect to F. Let K be the set of vertices in A2 that are reachable via an edge from L in R. We claim that gamma of K is equal to L because otherwise there will be a residual path from I in L to J in B2 minus L, thereby violating property 1. Let C of K denote the sum of capacities of all edges from S to vertices of K. Observe that all these edges are saturated in F', and that this flow must leave via vertices of L. Let EL denote the set of edges going from L to T. Let C of L and C' of L denote the sum of capacities of all edges in EL in networks N and N', respectively. By the argument given above, C' of L is greater than C of K. Since X is subtracted from all edges in EL in going from network N to N', C of L equals to C' of L plus the size of L times X. The total surplus of the edges in EL with respect to flow F is C of L minus C of K equals to C' of L plus the size of L times X minus C of K, which is greater than the size of L times X. Finally, since all edges in EL have the same surplus, each has surplus greater than X, the lemma follows. Theorem 5.8, the above stated algorithm computes a balanced flow in network N using at most N max flow computations. Proof: clearly the number of goods in the biggest piece drops by at least 1 in each iteration. Therefore, the depth of recursion is at most N. Next, observe that N1 and N2 are vertex disjoint other than S and T, and therefore the time needed to compute max flows in them is bounded by the time needed to compute a max flow in N. Hence, the total computational overhead is N max flow computations. Finally, as shown in lemma 5.7, the flow output by the algorithm is a balanced flow in N.